Hello, welcome to this video for AP Statistics covering the normal distribution and not only why we use the normal distribution, but how to use it and also how to use the calculator along with it. So the what you see here is a normal distribution. Why a normal distribution? That's kind of the first question we want to ask ourselves. Why normal? You have to think about all the different distributions that you could possibly have in the world when you collect data. You have some dot plots and some histograms here and just some other curves. Not all data is normal, but in the real world, a lot of data really is normal. So you might get some data and realize it isn't normal, and you will not be allowed to use a normal model. For example, this one over here is just kind of really flat and uniform. Hopefully you can see where my pointer is. The one on the top right there, that's uniform. You have data that's kind of skewed. You can see the stem and leaf plot. It looks like it kind of has a normal shape, but you'll see that it's kind of skewed to the higher numbers. This set of data at the bottom right is skewed to the lower numbers. This one in the middle left is what we call bimodal. So all these situations, if you get data like this, you're not allowed to use a normal model when you're trying to do probabilities. You should understand at this point, before you're kind of getting into this, understand what a distribution, a density graph is with a distribution that's in a density form, meaning that the area under the curve is equal to 1, where instead of having the frequency, let me maybe pull this, I don't know if I can make this bigger over the top. Yeah. Instead of having frequency on the y-axis, like we do here, you would have an actual decimal it would represent the percentage of the values underneath each of these bins. So you should be familiar with what a density graph looks like before this. The area under a normal curve that we use has an area of 1. And we're going to get to that in just a minute. But first things first, if you have a set of data that kind of looks like the one on the bottom left here that I'm blowing up right now, if you have a set of data like that, then yeah, you're going to use a normal curve. You're allowed to use a normal model in order to come up with your probabilities of things. Why am I talking about probability? Well, that's usually why you use a normal model. You want to find out how likely or how unlikely something occurring or not occurring is. So we use a model to try to represent the population. Like I might take a sample from the population and end up with something like this. But then if I want to extrapolate that to the whole population, we will just imagine, well, what if that really was a normal curve? And if I collected more and more and more data and I looked at the whole population, there'd be so many data points that this wouldn't be jagged anymore. It would just be a nice smooth curve. And that nice smooth curve would be the normal model. And then we could just look at the areas under those pieces to figure out what the probabilities are. Now, before we do that, you got to realize that you don't have to have a normal model to get probabilities. In fact, a lot of times we don't. A lot of times you're going to have a histogram like this. I'll try to blow this up again, and we can look at it, where I could count how many people or how many things are in each of these categories or each of these bins and add them up and say, well, from here to here, I have whatever, I don't know, I'm guessing here, like 375 people in that category. So the probability of randomly choosing a person or a thing in that range would be the 375 out of my total number. This happens a lot. We will take data and you could just use the actual data. Like, what do you do if you have something like this? Well, I would just take the data and use the data to count my probabilities. Like this is these are the actual grades from my geometry class last year for second semester, I think on the final exam. So if I said, what's the probability that a student of mine got below a 60 on their final exam? Well, I'd go 1, 2, 3, 4, 5 students out of the total number of students and come up with a probability or come up with a percentage. This was one class, I think. Actually, it's all my classes. But I could extrapolate that into, okay, so what about all my classes all the time, every year, right? It might not be the same, but I would kind of expect the distribution to be similar. So I could use this as kind of a model of what's happening in my class and come up with probabilities and percentages. And this happens a lot, not only when you collect a sample that isn't normal in shape. If it isn't a normal shape, I've just got to count it. I can't really use a normal model to estimate my things and come up with my probabilities. But it also comes up in simulations. So you'll see on my next slide here, I did a couple simulations. There's a lot of talk right now. I mean, there's been talk for a long, long time, but there's a little extra talk right now about racism and that kind of thing, and hiring practices and stuff. So I thought, I'll do a little simulation about hiring practices. So I tried on this first one. Let me actually pull up my TI Nspire so you can see this. So this is where I did the actual simulation. So I did a random integer up here, and I just tried to imagine, like, what if I was living in a city that had like 100,000 people in it? So I took out of 100,000, I chose 10 people to be my employees. And I know that, like, I grew up in Iowa. So let's say in Iowa, there's 85% are white, and I know that the other 15% are of people of color. So out of the 100,000, that means that there are 15,000, right, that are people of color, and 85,000 that are not, that are white. So I did a random integer, and then I just tried to I made a little formula. You can see my when statement down here. I made a little formula just saying, well, if this number is equal to or bigger than 85,000, then that means they're a person of color. So then give them a 1. So I tried to just track that, and I only did 10. So I said, let's just assume out of my 100,000 people, I choose 10 people to be my employees. And the whole idea is that if it is truly random, if I'm truly randomly picking employees, I want to know what that distribution looks like, because maybe someone's going to come to me as a boss, someone who owns a business, and say, "Hey, you're being racist because you don't have any people of color in your business, right? You don't have any employees that are of color, so you're being racist." Well, before you should actually do things like this. This is what stats is really great for, right? Is to find out the truth. What does it really look like? So what I did is I randomized this, and I would hit enter, and it would randomly pick all these numbers, and then it would add them up, and I could see how many people of color were there out of the 10. So there I got 1, I got 1 again, 1 again, there I got 2, 2, 2, 1, right? So then I recorded that down. I did it 100 times so I could see what the distribution looks like. This is what you need to be able to do for a simulation. And it's powerful because you can look and say, if it truly was random, if things are truly random, for a person who is choosing 10 employees from a city of 100,000 people, or from a pool of 100,000 people, where 15% of them are of color, 85% of them are white, this is what you would expect to see as your distribution if things truly were random. So sometimes you wouldn't have any people of color. A lot of times it would center around about 1 person of color out of the 10, and then sometimes 2, sometimes 3, and once in a while you'd expect to have 4 or 5 of those employees out of the 10 being of color. Now, so any one business could have anywhere from 0 to 5 people of color if it truly was random. Sometimes even more. If you did enough simulations, you would get, once in a while, you'd get a 6 or a 7 or something would pop up. Now people could argue maybe this isn't realistic because you didn't have 100,000 people apply for the job, right? So really, this should be taken out of all the applicants that you had, what percentage of them were of color, and then do a simulation based on that, right? So you could refine this, and I realized that when I was doing it, like, this really could be refined a little bit. I did another one just to see, like, I said, okay, instead of 100,000 people, I did, what if there were only 1,000 applicants? Now, I still kept it as 15% of the population are of color. So I just kind of said, well, let's say if of the 1,000 applicants, 15% of them were of color. But in this case, I chose 100 out of the 1,000. So I said, let's take 100 people and, just imagine that you have a bigger business. So I did it again. So out of 100 now, I'm getting 16, 14, 16, 14, right? And you can see that I listed it here and then ended up with that distribution. Again, very useful. It's like, okay, if I had a business that had 100 employees, then this is the distribution I would expect. And of course, yes, I would expect out of 100 that about 15 of my employees were people of color. But it could be down to 9 or even 7 or up to 23 or 21. So if you're someone who's investigating businesses to try to say that they're being racist or not, you should know your facts first. And then when you go out and look at businesses, you should have this image in your mind that, yes, some businesses will have 15, but some might have 23, some might have 7, not very many. You shouldn't expect to see that very often. But this is what the distribution looks like. Now, in this case, this is a normal curve, right? This would fit a normal model. So I could, if I wanted, go one step further and just say, well, let me represent this as a normal model that's centered around 15. And then I would need to know what the standard deviation is. So I'd have to calculate that and get the standard deviation. Okay, so I know that's kind of a big tangent, but I'm just trying to show you that sometimes you're going to see just the raw data. Sometimes you're going to see simulations. And sometimes you'll see the normal curve, or you'll see a curve that is a model of what you think the whole population would look like if you knew like every single data point. It's a model. It's a model. It's not the actual data. It's just a model of what you think the population is. And why is it so popular? Because there's so many things in the world that end up in a normal shape. Most things have kind of a center and then a little bit less and a little bit more, right? Um, the height of a person, maybe how much money you spend a week, what my, how fast I can run a 5K, just so many things have a normal shape to it. So that's why we use a normal model. We don't have other models. Like if it isn't normal, we're just going to look at the data just as it is and interpret it just as it is right in front of us, like that stem and leaf plot or that dot plot or that dot plot or that histogram or that histogram. We're just going to look at it just as it is. We don't have a different model that we can use. But if it is a normal shape, then we have this tool, this normal model that's really going to help us. Okay, that's what we're looking at right now. Like we're just going to use it and do probabilities. In the future, at the end of the year, we're going to use a normal model to talk about means of data sets and means of populations. And the difference right now, we're talking about one randomly selected item or person or thing. In the end of the year, we're going to talk about the mean of a population. And what turns out in the end, I won't go into detail, but what turns out in the end is that no matter what you start off with as your distribution, whether it's uniform or skewed or whatever, the mean, the set of means of a population actually comes out to be a normal model. So we're going to use a normal model at the end of the year, no matter what the original distribution was. Don't worry about it now. We're going to get into that later. But for now, like the big thing you need to put in your head is the normal model right now is not about finding the mean. It's about randomly selecting one person or one thing out of a population and knowing what's the probability that that thing is unusual in some way. Okay, so we get a normal model. You'll see right here, I have a norm PDF as the way that I graph this out. If you put that in your equation bar on your calculator, this shows it has a mean of 0 and a standard deviation of 1. So the top of the normal curve will always be where the mean is. And do you see how this turns from concave down? And right about here, we have an inflection point where it turns to concave up. The curve is different down here than it is up here. Right where that changes is where the standard deviation will be. That's it's made that way. So right where that inflection point is, that's where you'll have one standard deviation. So in this case, it's like 0.2, 0.4, 0.6, 0.8, and then 1. So 1 standard deviation is right there, and that's where it'll turn from concave down to concave up on a normal curve. So this is just the real basic one. We call it the standardized one with a mean of 0 and standard deviation of 1. Very basic normal curve. All right, but we don't always have that, right? We have other data. So how do we turn it into that if we have other types of data? This is called standardizing data with z-scores. Z-score is something we're going to use the whole rest of the year. So you're going to get very familiar with that. Let's do this problem, and then I'll talk about it a little bit more. So the first thing, let's say you have 2 data sets and you want to compare them. Like I want to compare how fast I can run a 5K versus how fast my wife can run a marathon. So we can't just directly compare those, right? You can't compare those. Yeah, they're different races. I'm male, she's female. I mean, there's all kinds of problems with trying to directly compare those. You just can't do it. It's apples and oranges. But using statistics and what we call z-score, you can normalize the data. We call it normalizing the data. And we can see how good I am relative to all the people in my category. And then I can also take her value, her time, and normalize that. And we'll get a score, a z-score, that shows how good or how poor she is relative to all the people in her category, females who run marathons. For me, it would be the males running the, what did I say, a 5K or whatever it is, right? Okay, so how do we do that? Well, you'll see the formula here. There's 3 different forms here. They're all the same thing, though. It's just that you see them a little bit different, written a little differently depending on what you're doing. Let's look at the one on the far right here, and this is pretty common. So we're going to take our data value. We're going to subtract the mean from it. So what we're doing is just finding out how far above or below the mean your value is, right? How far above. If I was doing weight of males or something, and let's say I weigh, 85 kilograms, but the average male weighs 95 kilograms, let's say, adult male, right? So this is 85 and then this is 95. So I would subtract those and get a negative 10. It becomes negative because I was below the mean, right? And you'll see that in a little bit here. So you're subtracting your value from, or the mean from your value to find out how far away from the mean you are. And then you're going to normalize that by dividing by the standard deviation. You want to say on average then, how far away from the mean is that in terms of standard deviations? So that's what a z-score is. It's unitless. The difference you get up here, like if I was doing weight, this was in kilograms, but my standard deviation would also be in kilograms as well. So you're trying to say, well, on average, adult males weigh 95 kilograms and their standard deviation is about, I don't know, let's just say 10 kilograms, right? So I would be taking that difference of 10 and, well, negative 10 and dividing by 10 because it takes 10 kilograms to go 1 standard deviation. And I would find that I was 1 standard deviation below the mean. So I'm 1 standard deviation below the average, which makes me a little less than average, right? But how far? Well, 1 standard deviation. So it's the z-score just represents how many standard deviations. The kilograms divided by kilograms cancel, and then you're done. You just get a z-score. Let's go into an example of that, all right? There's some, things on notes that you can read, pause and read. Okay, so here's an example of it. So Billy got an 80 on a test, but it's a different class than Susan's. Like Susan's on a different class, right? So he got an 88. The mean for his class was 84 and a standard deviation of 2.5. Susan got a 90 on hers. Her class had a mean of 86. This could be like Billy is like in math class and Susan is in French class. It could totally be 2 different types of classes. It doesn't even have to be math. Right? So we want to figure out how unusual each person is relative to their peers, relative to their class. So we take, for Billy's case, we take the 88 minus the 84 to get how far away from the mean he is. He's 4 above the mean. I divide by the standard deviation to find out how many standard deviations that is. So he's 1.6 standard deviations better than average. Susan is 90 minus 86 divided by 3.7. So then you end up with 1.1 standard deviations above the mean. So she's also better than average, but not as much as Billy. Billy's a little bit better relative to their peers. Remember, it's still not a direct comparison, but it is a way to compare apples and oranges. Like relative to all the people in my category or in my class or at my age level or whatever, this is how unusually large or small I am, right? And same for Susan. So Billy did a little bit better on his test than Susan did, because he was further away from his average than she was. Okay, so there's a few little notes and little things you got to get used to. When you like we already looked at the graph, right? So when you standardize, when you change things into z-scores, like you'll have a set of data. If we changed every single data point into z-scores, you would end up with this curve right here. You would have this. If you don't standardize it, then things start to shift. Like if you just take your data and you graph it as a normal curve without standardizing it, then like you had a mean of 2 and a standard deviation of 4. So your graph will just follow the data, right? So the peak of this is always going to be where the mean is, and the standard deviation. So if I went from 2 out to 4, 1, 2, 3, 4, that's where the inflection point would be, right? So I went 2 plus 4 to 6, right? And got my inflection point. So I can see where my standard deviation is. So let me go back one. So you can see a whole family of curves. The one in blue is the standardized one. If I took all my data points and I found z-scores for all of them and then I plotted them out, that's what you get. You get the blue curve. If you don't and you keep the means the way they are, like this has a mean of 2, this has a mean of 3, this has a mean of 3, this has a mean of 2, right? And you take the standard deviations along with it. Standard deviation of 1, 2, 2, 3, 3. Right? And you can see how the things kind of change, right? So if your mean is larger, your graph is going to shift over to wherever that value is. If your standard deviation is larger, your graph is going to spread out and it's going to shrink. Like it's going to get shorter, but it's going to get wider. Why? Well, it has to get wider to match the standard deviation. But why does it get shorter? Well, because the area under the normal curve has to equal 1%, or sorry, 100%. So in other words, 1, right? So if I were to add all the averages or all the area underneath here, it would equal 100% of your data, which is kind of weird to think about. That's something you can wrap your mind around a little bit. So that's why the area has to say 1. So if it gets wider, it's got to get shorter to match so the area doesn't change. When is the z-score big and when is it small? We saw that Billy was 1.6 and Susan was 1.1. How unusual is that? Well, it's more than 1 standard deviation away, so it's starting to get unusual, but it's not crazy unusual. But how big is big and what does that look like? So we have something what we call the empirical rule. If you go 1 standard deviation above and below the mean, then you will capture about 68% of your data. Again, this is a normal model. It doesn't work for all data sets. It doesn't work for uniform data. It doesn't work for skewed data. It doesn't work for bimodal data. It doesn't work for anything except data that is already in normal shape. Okay, but if it is in normal shape, then about 68% of it will be within 1 standard deviation. 95% of it will fall in between about 2 standard deviations, and 99.7 will fall into 3. So it's easy to see, like, if you're 2 standard deviations above or below the mean, you're getting pretty unusual because you're in that top 2.5%. If 95% is in the middle, that means that 2.5% is in the top and 2.5% is in the bottom little tail, these little red tails, right? I have another version of this. This is a different version. You can still see that in the middle here we have 68%, the 34 and the 34. If you added all these up, you get close to 95, right? And if you kept going, you'd get your 99.7 about. This one's a little more detailed than the other one. You don't need to memorize all these numbers or anything. This is what you should memorize: 68, 95, and 99.7. 68, 95, 99.7. Memorize that. You can figure out a lot of stuff just from those three numbers. But this does accumulate it for us. You can see there's a little accumulation at the bottom. These kind of break it into sections on the top. It's kind of nice to look at. It's a good kind of reference for you too. But we're going to use our calculator a lot to do a lot of these numbers and come up with these probabilities. But the reason we're showing you this is because we use the normal curve a lot to find out probabilities. What's the probability that of someone being as smart as Einstein, right? Well, Einstein had an IQ of, 150 or 100, I forget, 150 or something, right? Well, if you're doing IQ, the mean is at 100 and the standard deviation is 15, right? So this is 115, 130, 145. So if you're an Einstein, you're above 3 standard deviations. So that means that you're in that top like 0.01%, right? 0.001 maybe even, right? So you're way up there if you have an IQ of 150, right? So the probabilities is what we're looking for. What's the probability something happened? What's the probability that happened? Why is that so interesting? Because I want to know, like, if you want to tackle these big problems in the world, you want to know like what you should expect to see before you start calling someone liars or you start calling a business racist. You need to have the facts and you need to know what that really looks like. And it can be a powerful tool. You can take people to court because you can say, I know that this is the distribution I should be seeing and I'm not. So yes, I can call you. I'm not 100% sure, but I have reason to believe. I have reason to believe that you are being racist or that something is not the way it should be. So I want to look into that further, right? In statistics, we don't call people liars. We don't call people racist. We just say that we have evidence to suggest that something is going on that needs to be looked at. So the reason we're using this normal curve and doing all these probabilities is we want to know how unusual something is. If something unusual pops up, I want to know it, so that I can say, hey, that's really unusual. That shouldn't be happening. So I can look into it further and kind of get to the truth then, like what's going on, right? There's all kinds of things, medicine and people getting sick and just all kinds of things. Like, why is it, right? Okay, so this part is kind of just using this idea of probability in a normal curve. And then I'm also going to show you how to use the calculator at this point. Okay, so what's the probability of randomly selecting a data value less than 2 standard deviations below the mean? You can use the empirical rule because this is exactly 2 standard deviations. So if I remember this is randomly select one data value. So let me go back to that. We're going 2 standard deviations below the mean. So if I come to this and I go 2 standard deviations below the mean, then you can see my cumulative right here. So you can see it's 2.3%, 2.3%. If you did it on this chart, 2 standard deviations is right at that 95 zone, right? So 2 standard deviations below that is kind of 2.5%, right? 2.5% down here. And above would also be 2.5%. So we said on this scale, it was like 2.3%. Using the empirical rule, you get 2.5%, but that's close enough. So you can see I wrote down right here, 2.3% is what we ended up with. 2.5% is okay. Now I want to show you on the calculator how to do that. So let me go to here. I've done it already for us. I'm going to copy this down. Now I use Norm CDF, which you can see here. You can find that in the statistics tool kit under distributions. There's Norm CDF. You can use that. This will give you an area under a normal curve. You can tell it what your lower boundary is. Now I use negative 9999999, but you can also go down here on your calculator and hit the infinity button. So I can go from negative infinity up to -2 standard deviations because I'm going below 2 standard deviations. You put in your mean and put in your standard deviation. since I'm just using a kind of a standardized normal curve, I'm using 0 and 1. So the mean of 0, standard deviation of 1. And when you hit your enter, you get your 2.3%. So that matches what we thought it should be, right? Move this out of the way. Okay. So let's do the next one here. Sorry, hopefully you can see this okay. The next one, if you have an ASIJ bus ride that takes 35 minutes on average. I don't know what it takes you guys to come to school, but let's just say it takes 35 minutes to take you to school. But there's a standard deviation of 10 minutes. So that means, sometimes it's 25, sometimes it's 45. There's some variation going on there. So what's the probability of randomly selecting a bus ride, or, that today or tomorrow, what's the probability that tomorrow your bus ride is going to take you more than 45 minutes? Okay, so what we do is we find the z-score, and you have to do this work. There's a shortcut to find the answer. So if it's a multiple choice question, you can go right to the calculator and get an answer really quickly. But when you write these out on free response questions, you have to show your work. You have to calculate a z-score. So you're going to take the 45, which is the value you're concerned about, the cutoff, subtract the mean, which is 10, divide by the standard deviation, which is 10. So 10 divided by 10 is 1, and get your z-score. So this is 1 standard deviation above the mean. So again, whoops, let me go back to the empirical rule. So if I looked at this and I went 1 standard deviation above the mean, that's 68% in the middle, which leaves you with 32% left over, which is 16% on the top and 16% on the bottom. So it should be 16%, like right about 16% is what it should give me. If I do it on the calculator, I'm going to get 15.9%. So let's do it on the calculator again. You can see I've already done it up here. So I said, well, I use my norm CDF. What's the probability of having bigger than 1 standard deviation all the way up to infinity? So what's that probability with the mean of 0, standard deviation of 1? And you get your 15.9%. So really close to the 16 that we were thinking when we did it kind of quickly in the shorthand. Okay, let's look at and continue this on a little bit more. So what about a bus ride that takes 25 minutes? What's the probability, or what's the percentile rank? Well, that's the same thing. When you see percentile rank, they're just asking for what's the probability of that value or less. So we take our 25, subtract the mean, divide by standard deviation. In this case, we get a -1. So now I want the probability that our z-score is less than -1. Now notice on this last problem, I wrote this out, the probability of z being greater than 1. This is a style you got to get used to, and that we require when you're writing out free response questions. We want you to find the z-score. We want you to write out the probability. So here's same thing, write out the probability, and being less than 1 standard deviation or being bigger than positive 1 standard deviation is going to be the same area because it's symmetrical. So this has the same probability of 15.9%. So let's go on to the next question then. What's the largest duration for a bus ride that happens 10% of the time? So I'm looking for, 10% of the time, where's the cutoff for how long a bus ride it can be? Is it 55 minutes? Is it an hour? I want to know where 10% of the bus rides are really, really long. Where's that cutoff? So this is a little harder because I'm giving you the percentage, I'm giving you the area under the curve, and I want you to tell me what that value was. So it's kind of backwards from these other problems that we did. So first I need to know what 10% area is. So maybe on a graph, it kind of looks like this area over here is 10%. I just don't know where that cutoff is. So I'm going to go to my calculator, and I'm going to use a function called the inverse norm. Whoops. That can be found in the same place, statistics, distributions, and then right here you have inverse norm. Okay, so that inverse norm is what you want to use right here. So we hit enter on that, and we'll get 1.28. Now, what did I do? I put in 0.9. Why 0.9? Well, that's because I wanted the top 10% So on the calculator calculates the lower part of wherever your cutoff is automatically. So I put in 90% on the bottom half to represent 10% on the top half. It's the same thing. I still use 0 and 1, and I get my 1.28, right? Okay, so 1.28, that's the z-score. That's the actual z-score that I wanted. So it's telling me that 10% of my data is 1.28 standard deviations above the mean. 1.28. So that's like right in here somewhere. Well, I could estimate what that, percentage is, I guess. I mean, or that number is, but I don't want to. I want to calculate it. Why estimate it when you can calculate it? So I take my 1.28, which I got from the inverse norm, and I put it in my equation that I've been using all along. It's just that this time I know what the z-score is. So I'm just going to plug in everything else, and I'm looking for that cutoff value. So I saw multiply by 10, add 35, and you'll get 47.8 minutes. So 10% of, if this other information is true, where my mean is 35 and my standard deviation is 10, if that's true, then 10% of the time, my bus ride will take longer than 47.8 minutes, 10% of the time. Okay? So that's a really good problem. These are really good problems. You need to know how to kind of do these forwards and backwards and know them really well. You need to know why we use a normal curve. You need to know when is it appropriate to use a normal curve, and then what are the things you can do with it, like finding the area under the curve for probabilities, or finding cutoffs, like if you know what area you have or want, what's the cutoff to match that, right? Okay, thank you very much. There are other videos about like how to use your calculator more and other things like that, so look for other videos.